discuss a bit about implementation of strategies for digital design. And the main issue here is that in the last decades, chip complexity has grown faster than design productivity, which means that in the last 30 years, at least, the average growth rate of chip complexity in terms of number of transistors per chip on average has increased by 58% every year, and on the other hand, the productivity of designers, the so-called compound productivity in terms of number of transistors per person month that a designer can put on circuit design, has increased only of 21% per year. And this essentially means the fact that the number of designers working on the same chip has increased significantly, and at this stage, for a complex microprocessor, for example, the size of a team in terms of number of designers is of the order of 1,000 people. Okay, so a circuit that could be in the beginning of the 80s, the teams were of about 10 people. Now we had a 100-fold increase. And of course, in order to manage this complexity, it's also extremely important to have available proper design tools to be able to increase this productivity and also to be able to manage an increasing size of the team. So let's keep in mind these two aspects. First of all, every single designer must be able to do more, and still we need to be able to have procedures that allow very large teams of designers to work together. This is something similar that happened in the field of software engineering. It's quite similar, but also the type of languages and the platform had so changed in the field of software engineering that the teams have increased at a smaller pace. Okay. With hardware, the situation is a little bit more complex. Now, in practice, this increase in productivity of designers has not happened continuously. We have an average 21%, but in practice it happened in large steps. Every step had seen an increase in productivity due to the introduction of new design technologies. And actually, from the 70s, we had programmable logic arrays. Then we had standard cells starting in the 80s. Then the use of macro cells and module compilers later on, gate arrays, and more recently, reconfigurable hardware. All these steps really allowed a single designer to be able to place and put together circuits with a much larger number of transistors. We shall look at some of these technologies and at some of the, let's say, design approaches that are used today. Let's consider a complex digital integrated circuit, for example, a microprocessor. There are different categories of logic blocks. I'm just discussing in very broad terms. We have the so-called data path. The data path is the part of the IC where the computations are performed. Okay, in the data path we have all the arithmetics and all, in general, all the computation. All the combinatorial functions are also done in the data path, and so the structure of the data path is actually quite complicated, and the design is done by using customized modules, customized cells that can be done by using the so-called standard cells that we shall discuss in a minute. Okay, so the large logic blocks have been must be done ad hoc in a customized way for the data path, but the single elements that can be used to do that are standard cells. The other blocks are more structured. The control block is essentially a finite state machine that runs the microcode of the microprocessors, and it is typically done with standard cells. And then we have the memory. There are many different types of memory. We can have read-only memory, readable and writable memory. We can have memory with single port access or multi-port access. We can have DRAM, SRAM, non-volatile memory. There are many different types of memory. The main characteristics all the different types of memory have in common is that in this case the design is extremely well structured. We have very large arrays of every type of memory device we can consider. So in this case we have macro cells, very regular, and the productivity in terms of number of transistors that a single design can put on the chip in a given amount of time, in the case of memory, of course, can be very large. And the same thing is true for the last part, the interconnects and the input-output cells. In this block we have the on-chip buses, all the interconnects, and the blocks that allow the integrated circuits to communicate with the external world. Also in this case, the situation is extremely regular, extremely well structured, and a designer can put everything, every single cell in place quite quickly. Okay, so just when we look at this graph, let's consider also a type of communications that we have. Of course, the control block controls the operation of everything, so of the data path, of the memory, and of the buses and the communication with the external world. And on the other hand, the memory and the data path can talk with each other, and also put and read data that put to the external world and read data from the external world. So in terms of what we have discussed about the regularity of the procedure, this is some and this is a summary of what we had said. For the data path, we have the most customized structure. It's really ad hoc for the particular IC we are considering. The control finite state machine is somewhat regular, and both the interconnects and the memory part are very regular, have a very regular structure, very modular structure. Especially for the memory and the interconnects, we can, the design can go pretty fast by using semi-automatic placement and routing of the blocks. Okay? With placement and routing, we intend the placement, the position of the block on the floor plan of the chip, and with routing is let's say um, the design of the paths for the interconnects. Okay, the design of the different paths for all the interconnects that are needed between the different blocks. Of course, we need to, let's say, minimize the total path. We have different blocks that must be connected, and I mean, there is this optimization problem of placing the blocks in a proper position and putting the interconnections in a way as to minimize the total length of the interconnect in order to improve the performance of the chip. Okay, now where do we go from here? It's important to put an accent on a particular two particular types of distributions, of signal distributions, that are extremely critical in integrated circuits. One is the power, and one is the clock, and the other one is the clock. Because the clock signal and the power must be provided to every single logic gate of the whole chip. And therefore, those two types of distributions are actually critical, are the most critical ones for the chip. Okay, what's the main effect of using tools for increasing the productivity of designers while at the same time largely increasing the number of transistors per chip? Okay, in order to have let's say a visual idea of the effect, let's consider the layout of the Intel 4004. If you remember, this is the first microprocessor by Intel. We mentioned it at the beginning of this series of lecture. It's a simple microprocessor, the first microprocessor fabricated by Intel. It contained a little bit than 2000 PMOS with a 10 micron process. So if you look at this, the total area is 4 millimeters by 3 millimeters, and if you look at the image of the chip, you can see that it's pretty clear that it is made ad hoc. So actually it was designed by hand, transistor by transistor, on a large sheet of paper. Okay, this is something that could be done at a time. There are some regular structures, but they are quite limited. If you this structure is regular. Let me use the highlighter. No, not the highlighter, the pointer. This structure is pretty regular. This other structure is also pretty regular, but the rest is really, let's say, done by hand, and it is clear that it's done by hand. Also, the interconnections, they're not so regular. You see more or less they run around the periphery of the integrated circuit. Okay? If we look at the following generations of microprocessors from Intel, let me just show them here, you see the structures become more and more regular as time passes. This is the Intel 8080. You see there is a larger regular structure here. This is the 8085, a large structure. I mean, this is clear. This is the 8486. I mean, they're not so recent, but you can see that there are many, many more regular structures, and this is due to two main reasons. One is automation in the placement of big chunks, big building blocks. Mostly the memories and the I/O blocks, and the fact that in doing so it is possible to manage a much larger number of transistors. In the more recent microprocessors, this is something that probably I have already highlighted. You should consider that much more than half the area is occupied by the caches that are static RAMs with an extremely regular structure. Okay, so that part is easy to design and to deploy, because of course it's an array of all identical cells. Okay. Now, another concept that we need to discuss is the trade-off between flexibility and efficiency, because this is a typical trade-off in the design of a digital system. When I say flexibility, I mainly mean programmability. Okay, and the trade-off is pretty clear. On the one hand, flexibility has two big advantages. The first is that, of course, we can reuse the design for multiple applications. If we have a flexible block, we can reprogram it and use in another piece of hardware, using an identical piece of hardware with a different configuration or with a different program, and we do not need to redesign it and to pass all the fabrication hurdles. And then another advantage of flexibility, of course, is the possibility to upgrade the hardware by only changing the software. So if we need to change the operation of a block, we just need to reconfigure it or to reprogram it. Okay, these advantages are pretty clear and apparent. Of course, there are significant disadvantages too, and the main disadvantage is the performance loss, in the sense that the flexibility, the reprogrammability, adds a lot of overhead and slows down the operation of the chip. Essentially, because if there is for each operation a phase of instruction decoding, just to take an example, this instruction decoding, of course, takes time and slows down the operation. And for the same reason, we have a significant increase in energy consumption. Okay, so this trade-off is pretty clear, and how do we play with the trade-off? Of course, we have different degrees of flexibility and, on the other hand, of efficiency, and depending on the application, we can choose one or the other. At the top, we have a custom hardwired solution, so something that is completely fixed at manufacturing, a digital circuit that performs as designed, but in which nothing can be changed. Okay? In that case, we have the lowest degree of flexibility, but we have typically the best possible performance and the best energy efficiency we can get. Okay? If you consider these steps, we're really talking here about one order of magnitude for each step. So this means that if this is 1 in energy efficiency, in energy consumption, the next is 10, the next is 10 to the second power, and the next is 10 to the third. And this is actually if we consider, for example, the energy consumed for the same operation. Okay, so the next step is the reconfigurable hardware. In this case, we do not have a real reprogrammability. We just have some parameters that can be changed. Okay, for example, some tuning parameters, some variables written in registers that can be changed. Okay. In this case, we have an increase in flexibility, but a loss in energy efficiency of 1 order of magnitude. Then we have the application-specific processors. For example, the DSP, if you want, the DSP stands for Digital Signal Processor. It is a processor dedicated to signal processing. And in that case, let's say, of course, we have something that is completely programmable and that is also specific for the applications, in the sense that it has some specific hardware particularly optimized for the type of application, in this case, signal processing. But the important thing to consider that compared with a digital filter that is hardwired, that cannot be programmed, that is fixed once it's done, the digital signal processor increases the power consumption by 2 orders of magnitude, let's say as a rule of thumb. Okay. Of course, we have a large increase in flexibility, but we pay for that. Okay. The same is true for other application-specific processors, such as the GPU, the graphic processing unit for graphics. Okay, and then the highest degree of flexibility is with an embedded processor. Of course, in that case, everything is completely programmable. But of course, we lose another order of magnitude in energy efficiency. Okay. There is also another aspect that I want to underline that is connected to this consideration, that is related to the scale of production. Because, of course, if we want a custom hardware solution, we have to do it, let's say, let's talk about us, we have to do it all ourselves. So it means making a specific, if I make the example that I made before, a specific digital filters on our own. So it means designing and then fabricating a chip with those characteristics. Of course, that is doable only if we plan to do it at a large scale. If we plan to fabricate several thousands of chips at least, so that we can, let's say, we can divide, we can share development costs over a large number of chips. On the other hand, if we adopt a flexible solution, such as an embedded processor, we do not need to fabricate it. We just need to buy it. Okay, so the same. So we do not have any upfront costs to sustain in terms of scale of production. So in addition to flexibility and energy efficiency, the other consideration that is still on this scale is the scale, the number of integrated circuits that we need. Okay. The larger the number of integrated circuits that we need, the more convenient it is to go towards the top of this list. Okay. The smaller the number of integrated circuits that we need, the more convenient it is to go to the bottom. Okay, since I mentioned these aspects related to cost, it's significant to make two very simple considerations regarding costs. So when we consider the cost of an integrated circuit, we have to consider two different types of costs. One is variable costs, the so-called recurring expenses, and the other one is the fixed costs, the so-called non-recurring expenses. Okay, the name is let's say, self-explaining, and from the point of view of understanding how these costs impact the cost of a single integrated circuit, we have to consider that the fixed costs are those costs that are independent of the sales volume. Okay? For example, the development costs, the design costs, they are totally independent of the number of integrated circuits that are produced. The variable costs are those that are proportional to the volume of sales. So proportional to the number of integrated circuits that are actually fabricated and sold. So with this distinction, it's pretty easy to consider a cost and to put it in one basket or in the other. Okay. Of course, the cost of one chip is equal to the variable cost of that chip plus a fraction of the fixed cost. And the fraction is the fixed costs divided by the number of chips that have been fabricated. Okay? And this is the factor in which the number of the scale of production, the number of chips fabricated, enter into consideration. Okay, because if this denominator is too small, the fixed cost, of course, can matter a lot and be predominant. Okay, there are other additional things that we should consider. Let's consider the categories of costs. We have among the non-recurring costs mainly the time and person months required for the design. So there are some salaries to pay of all the people is involved with the design, and those costs are independent of the number of chips that will be sold. Okay, of course they are fixed costs. And then there is the production equipment related to the specific chips. If we consider a fab, let's say a so-called integrated device manufacturer, which is a company that designs the chip and fabricates them. Of course, there's the production equipment, the fab, which has to be put in place independently of the number of chips. Okay. The recurring expenses are can be decomposed in a number of contributions. Of course, we need to sum up the cost of the die, of the single silicon die, plus the cost of the die test after fabrication, because every single chip must be individually tested. Then, of course, we have to sum the cost of packaging, and then we have to divide over the final test yield. The yield is the percentage of good chips. Okay? If you remember, I mentioned the fact that the yield can change a lot during the different phases of a production of CMOS technology. At the beginning, it is pretty small and then increases. But the yield has a significant impact on the recurring expenses, because basically all the costs depend on the number of chips fabricated, and then if you have a yield of 50%, it means that you have to throw in the basket 50% of the chips that you have fabricated, and therefore the cost has to be divided over a smaller number of chips. So the yield is an extremely critical issue in determining the cost of a chip. Then, of course, once we have the non-recurring expenses and the recurring expenses, we have seen the formula for calculating the cost of a chip. Now, the cost of a die, is not immediate, because that also depends on the cost of a wafer, because the process, the fabrication process, as I mentioned during our last lecture, we basically the process occurs wafer per wafer. So we need to, we know from a fab the cost of processing a single wafer. Then we have to divide this cost for the number of dies per wafer, and then we have to consider the die yield, which is the percentage of good dies. Okay. The dies that are not good are those that when during the cutting, or because of some dust in the cleaning room, or because of some errors in the processes, I mean, have to be discarded. Okay, and just from a morphological inspection, they are seen as to be not good. Okay, so there are two phases in which dies can be discarded. First, during fabrication, after just a morphological inspection, physical inspection, and then after complete fabrication, after an electrical test, a functional test. Okay. So one thing that is pretty critical is this die yield, because the die yield is something that depends a lot on the process, and also depends a lot on the size of the chip, on the area of the chip. Okay, this is pretty intuitive, because of course if you consider one of the main causes of error, for example a dust particle, in that case it is clear that the larger the area of the chip, the higher the probability of having a dust particle on top. Okay, that is pretty evident. But also any other type of error with the lithography, or with the etching, or with the other processes that we have seen, of course increases as long as the area of the chip increases. And there is an empirical formula that is typically used for estimating the die yield, which is this one. You see, its die yield is 1 plus the number of defects per unit area times the die area. So this numerator is the average number of defects per die, over alpha, and everything to the power of minus alpha. Okay, and this alpha, this is an empirical formula. It's something that matches the statistical analysis done on non-functioning dies, and for CMOS processes this alpha is typically 3. So just to have an idea, by looking at this the behavior of this expression, it is pretty clear that the area has a huge impact on yield. Just for example, I plotted this graph, is the formula by using 1 defect per centimeter squared in this here I put 1 per centimeter squared. In the place of alpha I put 3, and then I plotted the die yield as a function of the die area, and the die area here is expressed in square centimeters. Okay, so of course the smaller the die, the closer the yield to 100%. But if you look at this behavior, it goes down pretty fast. Okay, for example, if the die area is 2.5 millimeters squared, which is the first number, the yield is about 99%. if I go here to 2.5 centimeters squared, the yield is something like 16.2%. Okay. So, and basically this expression gives the larger size that we can have of an integrated circuit. So the fact that the size of an integrated circuit in time has not grown beyond something like 2 centimeters squared is the fact that we have a strong decrease of die yield as a function of area. Of course, if we want to make and to sell with profit a microprocessor with 2.5 square centimeter of area, of course you need to have much less than 1 defect per unit area. Okay, you need to move quite up to the 70–80% range. Okay, but this one is typical of many processes. For example, it's typical of the processes that we use in fab in Taiwan for designing chips. Okay, so but we have all the elements that we need to be able to evaluate the cost of a chip starting from a set of numbers, and this is done, of course, continuously in order to know what is the break-even point in the selling and in the production of a chip. So I mentioned this aspect mostly to stress the importance of yield, the importance of the impact of device area on yield, and the relative impact of the fixed costs and of the variable costs, because in many cases the type of solution that is used for a given problem depends on these considerations. Okay, now what are the options for the approaches to implement digital design? Of course, one of the options is custom design. And custom design means designing a circuit transistor by transistor. Okay, just by putting every transistor in place. This is, of course, the more basic and more time-consuming mode of operation. And, just if you want to make a metaphor, is exactly like making software development in machine code. Okay, is exactly the same thing. If we want to make a comparison, and it's very common for some specific applications and for some applications that really need to be fast. Until the 80s the beginning of the 90s, actually it was the most common way of designing a digital circuit for specific applications, at least. Okay, for large microprocessors, one could reuse some blocks, but for many circuits for specific applications, it was the only way to go. And of course, it is really expensive in terms of person months, in terms of time. Then, of course, all the other approaches are called semi-custom design. Semi-custom means that you can use pieces that are pre-made and then can be used. And at the present time, semi-custom design is, of course, much more common, also for large projects. Okay, with semi-custom design, we have really many different possibilities. One possibility is the so-called cell-based semi-custom design. In that case, we used the so-called standard cells, which means that we have a library of individual cells, for example, logic gates, buffers or sometimes also analog blocks that are needed for the operation of the devices, input-output blocks, etc., that have been pre-made, have been put in a library, and must only be used. Okay, this library is called, of course, a library of standard cells. Okay, and this is the option that I mentioned. Then we have so cell-based can be standard cells, that one that I mentioned, and can also be macro cells. In the case of macro cells, we have macro blocks. Blocks that are much larger than the single gates and the single buffers and so on. In the case of macro cells, we have, for example, LSI circuits, such as a decoder, a large multiplexer, a complete encoder, blocks that contain between 100 and 1,000 circuits. But we can also have much larger macro modules, such as a memory bank, a non-volatile memory bank that we keep, that we take as a whole, and we put in a chip. And of course, these macro cells are very often reconfigurable, so that, for example, in the case of a memory bank, we can let's say configure a memory cell, choose a memory cell, a memory bank of 1K bit, for example, and move it to the design. Of course, this procedure speeds up a lot the design. And on the other hand, we have array-based semi-custom design. In that case, we have typically an array of cells that have been already deployed on silicon, and in the case of the so-called gate array semi-custom design, we only need to put the interconnections. Okay. And in the case of the so-called reconfigurable logic, the FPGA that we will discuss a bit later, in that case we need to let's say program some logic in terms of, for example, lookup table, and but we have some slides to discuss. So in the case of gate array, the important thing to keep in mind is that in the case of gate array, we have several logic gates already deployed in silicon, and we only need to design the interconnections. Okay? In the case of reconfigurable logic, we have some, as the words say, reconfigurable logic that is already in place that we need to program and to configure in order to let the circuit perform the operation that we want. So it's a much wider spectrum, and also in this case I would like to stress the fact that we have let me just use the pen here, that we have an increase in flexibility when we go along this direction. And we have an increase of energy efficiency in the opposite direction. It's not working. And since we also discussed the costs, okay, the other thing that is important is that when we go in this direction, we have an increase in the recurring expenses, because the single chip of FPGA costs a lot more than a single chip made in standard cells. And we have in the other direction, let me see if I can, an increase in the non-recurring expenses. because of course the design of a chip with standard cells is much more complicated than the design of a chip made with FPGA. Okay, these are the directions that we have to consider, and that of course depend on the particular application we have in mind, on the particular application, in the particular market also, because independent of application, the size of the market counts. Okay, just to go a little bit into some more details about the four options that I mentioned. With custom design, I mentioned we make a transistor by transistor design of a complete circuit, and this is the way to achieve the best possible performance with a semi-custom design, and also typically, as I mentioned, the best energy efficiency. It's of course time consuming because we still have to design the complete circuits in terms of single transistors. So we have a high cost of design in terms of person months of people and time, and high time to market, which is a different consideration, but it's important for different aspects. Independent of the costs for the design, the window of opportunity for putting a chip on the market is typically pretty small, because of course on the one hand the technology can evolve, on the other hand a competitor can enter the market, and therefore the time required to design a chip is something that reduces the time during which the chip can generate profit in the market, and therefore it's critically important especially in applications where there is a competitive market. It's critically important to have a reduced time to market in order to be able to arrive first with a solution and to obtain much of the profit before another competitor come, and of course prices go down. So when custom design is used, of course it is used for blocks that have to be used many times. This is critical. For example, I mentioned before the standard cell type of designing, but somebody has to do the standard cells, okay, because they do not come naturally from the process. And typically the standard cells are designed with a totally custom design. But of course this can be pretty convenient, because of course standard cells, library cells, are used in a lot of designs with the semi-custom design approach. And so in that case it's necessary, because you do not have standard cells available when you design the standard cells, and is convenient. Okay. And this is typically something that is done every time a new technology comes to the market. When a new technology, for example, in this period, the 10 nanometer technology is coming to the market, and there is a team spread over the whole world that is designing the standard cells for the 10 nanometer process. Okay. The closest is in Sophia Antipolis, near Nice. Here there's a team by Intel which is designing the standard cells for the 10 nanometer process. Okay. Then it's something that can be done for very high volume ICs, such as microprocessors. Of course, for example, in this case, Intel is doing for its own microprocessors. And of course, when cost is not an issue, and also time to market is not an issue. And this is typically the case for defense applications. Defense applications, the volume is small, but there is no actual constraint on cost. So these are things that I already mentioned in discussing the main block. Just is useful to have them here. In the so-called cell-based semi-custom design, we need a library of cells. We can use standard cells, that is the simplest case, or we can use the macro cells, which are, of course, larger circuits. And here I mentioned also mega cells, because now it has become also quite common to have a complete microprocessor as a macro cell to be included in a more complex chip design. So, for example, yeah, that is the case for example, microcontrollers for specific applications. One includes the microprocessor and microprocessor from ARM, for example, as a macro cell, and then includes in the chip all the other peripheries that are needed to obtain the microcontroller. Also, digital signal processors or specific interfaces such as the PCI and other interfaces are pretty complicated. They can actually contain millions of transistors, and they can be included as mega cells. Mega cells are simply large macro cells. Okay. Now, just to understand how a standard cell design work, this is a picture of the layout of a standard cell integrated circuit. So let me just illustrate it. It is a pretty simple circuit actually, but at least it can be clearly understood. Of course, this is this square is the layout. These are the I/O pads. So the contacts with the external pins of the chip, and this area is the area with the standard cells. This row is a row with standard cells. The other black row is a row with standard cells, and in the middle there is a routing channel. So this is a picture that should explain the same thing. So every standard cell is done obtained with the same height, and they are placed one adjacent to the other in a row. And then they have the input and output contacts on the border, on the bottom side or on the top side. And then we use the channel in the middle, that is called the routing channel, in order to connect. So the work of the designer when working with standard cells is to place the standard cells in these dedicated rows, and to connect them using the routing channel. And of course, this procedure can be somewhat automated. So the placement of the standard cells in the rows can be automated, and also the interconnections can be somewhat automated. Okay. So one can obtain complete automation or guided automation depending on the difficulty of the design, because of course with the complete automation one can only get to a certain degree of optimization. So this is the first generation of standard cells up to the 90s, let's say. In the more recent generation, the design is much more denser, because there are essentially no routing channels. This is a standard cell with a new generation from 2000 and on. You still see the rows, but you do not see the routing channel between them. And the reason is because the higher level of metal are used for interconnections, and therefore you can see this is a row, this is another row for the standard cells, but now the interconnections do not occur towards the periphery, but by passing over the standard cells, for example, from level metal 3 or level metal 4. So the interconnections are on top of the standard cells, and there is much better use of the total area of the chip. Again, one can exploit a significant degree of automation also for the placement, also for checking that actually the design behaves as it should be. Okay. So, independent of the type of custom design that is used, or semi-custom design that is used, in order to, let's say, manage the complexity of the chip, it's absolutely required to start the design at a high level of abstraction, and then to go down from this high level of abstraction to the physical design of the chip by using tools that enable us to check that every step is correct. So what does it mean in general terms? First is that the behavior of the circuit is first designed and tested using a so-called hardware description language. So a hardware description language is typically a C-type, C-like type of language that enables to describe the operation of the hardware and the operation of the different blocks in a way that is pretty similar to functional programming. Okay, so every block is described as in software a function is described, and the relationship between blocks is described in a way similar to the relationship between different functions. In the part of the class by Professor Fanucci, you will go into some more detail about this aspect of the hardware description language that is common to all types of semi-custom design. Then there are logic synthesis tools, so that are basically automation tools that are able to obtain from the hardware description, in terms of a hardware description language, to the gate level description of the circuit. Okay, and to check that the circuit described at the level of single gates behave exactly as the circuit described with the hardware description language. So, with logic synthesis tools, we arrive to gate level design. This is let's say, the first step. Then, when we have a gate level design, in principle, we are able to use a set of standard cells in order to design the circuit. But of course, if the circuit is complicated, the placement and the routing, the placement of the standard cells and the routing, the placement of the interconnections, is not something that can be done reliably manually. And then it is done with so-called placement and routing tools. And these tools can do everything in a completely automatic way, or can be guided by the designer. Can propose different solutions or do one step at a time with some check from the designer. And so after that, we arrive to a standard cell layout. Okay? And that is basically done, because when we have the standard cell layout, for every standard cells we already have in the library the layout and the set of masks that are required. We only have to put everything together, and and this can be done just with a touch of the button, because of course can be something completely automated at this time, and go to Foundry. So the most relevant tools are in this line of design: the logic synthesis tools to go from hardware description to a gate level design, and the placement and routing tools. Okay, this is the example at the standard cell level, but also with the macro cells is exactly the same, and also with the FPGA it is pretty similar, only we do not have to place and route, because the placement is already done. We need to make the configuration. We have a configuration tool, not a placement and routing tool. But let's say the sequence of steps is exactly the same. Okay, this way of designing a chip is very suitable to an industry model that has been very common in the last 15 years, and is the so-called fabless model. What does it mean? A fabless company is a company that basically does everything for the production of an integrated circuit except the fabrication. Okay, so we typically have 4 different steps to obtain a chip. We have the design, then we have the fabrication, then we have the testing, and then we have the sale. Okay, the 4 steps. Now, in order to distinguish them from fabless company, a company that does all these steps, that starts from silicon until, and it goes from the initial ingot of silicon to the sale of integrated circuits, is called an IDM. IDM stands for Integrated Device Manufacturer. Okay, and for example, integrated design manufacturers are Intel, ST Microelectronics, the Franco-Italian semiconductor company, is an IDM. Samsung is an IDM, and few Texas Instruments is an IDM. I did not mention it, but of course that also is an IDM. There are many few of them, because now it's the fabrication part has become extremely expensive, as I discussed, just because the fabs are extremely expensive, and their investment can only be justified for very large volumes. The fabless model is essentially a fab, a company that is equal to an IDM, except for the fact that it does not fabrication. Okay, does not do fabrication. And in order for the fabless company to exist, we need also the foundry companies. Some companies that only do fabrication. Okay, so a fabless company does the design, the testing, the design, then sends the design to the foundry, and the foundry fabricates the integrated circuits and sends them back to the fabless company. The fabless company makes the testing and the sale. Okay, so of course in this relationship, the foundry has to provide the standard cells for the fabless company, because the standard cells can only be designed and verified and tested by who has the means of fabrication. And as I mentioned, this fabless company model has become very popular in the last 15 years. There are some names that you probably have heard of. For example, Qualcomm is a fabless company. It's probably the largest fabless company now. Qualcomm makes is the number one producer of microprocessors for smartphones, for Android smartphones, the Snapdragon series. Okay, Snapdragon, yeah, Snapdragon series, and that is a completely fabless company. Everything is fabricated outside. They do all the design, the testing, and the sale. Okay. The other names you probably that you might I put some examples here. Here, Altera and Xilinx are two FPGA companies. They produce field programmable gate arrays, and they also are completely fabless. Most of these companies have their chip made by three foundries. TSMC, which is the largest, is the Taiwan Semiconductor Manufacturing Company. UMC, which is another company in Taiwan, and SMIC, which is a Chinese company. And that's it. Another actor in this model, which has become very relevant in the last few years, is the so-called IP vendor. The IP vendor essentially sells only the design of microcells. So it sells a library, typical large blocks. It can be a complete microprocessors. For example, the largest IP vendor that we have now is ARM. ARM sells the ARM architecture in various different models and possibilities that are included by the microprocessors producer. For example, I mentioned Qualcomm. Of course, Snapdragon processors are based on the ARM architecture. Then Qualcomm has to use the standard cells from TSMC for the production, and the microprocessor architecture from ARM. Okay? Then puts everything together, designs the complete microprocessors, sends it to the foundry for fabrication, gets it back, and sells it. Of course, just before I switch to another aspect, the reason why this fabless company has become so successful is the fact that you remove all the investment costs. Because if you do not have the fab, basically you do not have to buy all the equipment and to maintain a fab. The only non-recurring costs that you still have are the design costs, that typically are much smaller than the cost of building a fab. Okay. And on the other hand, the foundry can go on because they can fabricate for many different chips for many different companies, and they can go up in scale. And going up in scale is the only way to keep the high fixed costs under control, because they have large fixed costs but produce billions of chips for many different companies, and therefore can divide all these fixed costs over a large number of chips fabricated. Okay, by splitting the industry in two different types of companies, things have become much more efficient, and therefore the model has become successful. The only IDM that are still around are those that consider really strategic to have the foundry inside the company. For example, Intel and Samsung use their specific competitive advantage the fact of having their own fab, because they are able to make advanced processes available only for their own chips before the competition. Okay, and that is a strategic competitive advantage in order to sell first with the high performance devices. regarding macro cells and macro modules, it's important to distinguish between two different types of macro cells, the so-called hard macro cells and the so-called soft macro cells. And so this is another important aspect of the chip design. So hard macro cells are custom designed for a specific CMOS process. So basically we have the circuit with all the transistors with the dimension, with the proper dimensions, and with the layout of the various masks already done. Okay, so we have a predetermined functionality of the macro cells and also a predetermined physical implementation. Okay, what is the advantage of doing that? Is that we have a total optimization of the macro cells for the process. It works, and it works better than in another way, because if it is, for example, a microprocessor can be a memory bank or it can be a complete microprocessor. It has been optimized for that specific process, so you can put directly it into the chip and it works perfectly. The problem is that since we have a technology change every 2 years, if there is a technology change, the design must be thrown away. It cannot be reused. Because of course the characteristics of the transistors have changed, and therefore that design is useless. Okay? The other option is to have soft macro cells. Soft macro cells are software essentially, and are written in a way, are only a gate netlist. So it's CQ specified in terms of gates, and then this means that we have a predetermined functionality, but the physical implementation is not predetermined. So one gets the gate netlist and then introduces it in the design flow at the when the total gate netlist is fabricated. Which means that then from there, if we want to go from the soft macro cell to the complete design, we need to implement the gate netlist in terms of the standard cells of that specific process, and then to do the placement and routing and so on. So we have something that is less optimized and less complete than the case of hard macro cells, but of course it's independent of the process that we have, because still the synthesis from the gate netlist to the physical implementation has to be done with the rest of the circuit. Okay? So if there are aspects that are not clear, please ask me. And for example, I mentioned ARM before as an IP vendor. Typically, ARM provides an ARM architecture, a complete microprocessor as a soft macrocell, which is then physically implemented using the standard cells of the foundry. Okay. This is an example of a macro module. Is an 8K static RAM. In this case, you have there is a module generator which is completely configurable. You put in the configurator how large you want the memory, and then it gives you the not only the gate netlist but also the layout of the chip. You have just to take this and to put into the chip. Okay. And then with some soft macro modules or IP, basically you have a piece of code which is a gate netlist, a list of all the gates and then the connection, the interconnections that make the soft macro cells, and then all the rest in terms of choice of standard cells and of placement and routing has to be done in the process flow, in the design process flow. Okay, so just to summarize, some aspects. This is similar to what we have already discussed before. There are here, no, sorry. There are two different steps. Here we have a functional implementation. Let's write here functional. Functional implementation, we have different phases. First, we have the so-called design capture. We use a hardware description language such as VHDL. HDL stands for hardware description language, and some IP blocks if we need them from an IP vendor in order to describe the behavior of the integrated circuit. Then we need to use some logic synthesis tools. So we have a logic synthesis step, at the end of which we have a gate netlist and all the constraints for placement and routing. What are these constraints? The issue is essentially this. The length of an interconnections is associated to a delay of the interconnection. And of course, in the logic synthesis, there's a maximum delay associated to the interconnection of a given gate, output of a given gate to the input of another one. So there's a maximum delay associated from one for the sending of the signal from one gate to the other. And this delay, this maximum delay, puts a limit on the maximum length of the interconnect. And this is the routing constraint. That of course has to be taken into account in the placement of the different blocks on the chip. So these are the placement and routing constraints. So, but when we have a gate netlist, we can make a pre-layout simulation and verification. So we can make a simulation of the chip before making a layout, only on the basis of the gate netlist. We know all the gates that compose our digital circuit, and therefore we are able to verify the operation of the circuit. So we make a check after the end of the pre-layout verification. If after the check the circuit does not work as expected, we have to go back and to understand what's wrong and to redo this step. Okay? If it works, then we are done with the functional implementation, and then we can move to the physical implementation. So at this point, I don't know what's wrong. At this point, we know that the gate netlist is working. That logically, from a logical point of view, everything is working correctly. Now we need to implement everything physically. And what do? First, we do the floor planning. Floor planning means putting the standard cells and the macro cells on the die, at a certain position on the die. It can be on the rows of the standard cells. And then we need to place and route using the constraints that we have already obtained. These constraints have to be used as inputs in this part. At the end of it, we have the complete layout of the chip, and therefore all the masks for all the fabrication processes. So we are done if everything works, but we have to check if everything works. And then there is a procedure that before sending everything to production starts from the layout and the masks and verifies if the chip works properly. So starting from the layout, we have an electrical circuit extractor, which is a tool that extracts the associated electrical circuit from the knowledge of the layout. And then once we have the electrical circuit, we can perform a post-layout simulation. So a simulation of the extracted electrical circuit to verify if it works according to specifications. Okay. If it works according to if it does not work according to specification, we go back. We just need to go back here because we know already that from a functional point of view, it's working. Okay. If it works, we can just send to foundry for fabrication. We are ready to do that. Okay. This is just to make the sequence clear. And then we can be pretty confident that if the tools are in place and the models of the transistors and the models of the technology process is correct, then if it works in post-layout simulation, it will also work in the actual physical implementation. Okay, I mean, and this really requires that all the models that are used in the simulator are as accurate as really possible. Okay, some more details about the array-based implementation. The other part, we have a cell-based implementation and the array-based implementation. In the array-based implementation, the most important aspect is that we do not require a complete manufacture run. We do not need to go to the fab for a complete run. So we have two possible solutions, if you remember. We have a gate array solution, which is sometimes also called the C of gates, and we have a field programmable gate array solution. So the gate array solution is actually used to be much more popular a few years ago. Now it's not as popular anymore, and it basically consists in this. We start from wafers that have been partially processed. Everything has been processed except for the metal interconnections. So only the metal interconnection steps are needed. We have an array of different gates assorted in different ways according to very different algorithms. So we have several inverters, several ANDs, several NOR, some memory banks around the chip. And we only need to interconnect them, okay, in order to realize the operation of the circuit. So instead of having the placement and routing step that we have with the standard cell, in this case we have the placement of interconnects only. Okay, so this means that once we, from the design point of view, design the interconnects, we send the design of the interconnects to the foundry that has already the wafers ready and only has to perform some final processing steps in order to put the interconnects. Then they cut everything and send back. Okay. So of course, the fabrication steps for the interconnects are the easy ones. Okay, easy. I mean, in brackets, not that easy, but they are done at relatively small temperature, and they scale pretty well. So one can really cut down a lot the costs. Okay, of course, you can imagine that from the design point of view, you use what you have in terms of logic gates, so the design is not going to be very optimized, but it's a way to cut costs down. In the case of field programmable gate array, the situation is very different, because in that case, nothing goes back to the foundry. There's a complete separation between the manufacturing phase and the implementation phase. We have a so-called FPGA, a field programmable gate array, out of the fab, and then we only have to program the interconnections or program some memory. Typically, this is what we have to do, and we do it out of the fab. And this is done when the final product is done. Of course, the huge advantage is that in the manufacturing phase we can have very large volumes, because they can fabricate FPGA for everybody, for an extremely large number of companies. They want to do completely different things with this thing. And of course, we have an extremely low time to market, because we just need to order the FPGA. It arrives, and in 2 days you have the FPGA. You can program it, and in a few days you are out with a chip that is completely working. You have very low non-recurring expenses. You typically have a high recurring expenses, because these FPGA are very costly with respect to similar integrated circuits in terms of capability. Okay, and this is due for different reasons, and one of the reasons is the fact that, of course, you can never be able to exploit completely all the computation capabilities of the FPGA. So you have a much larger number of transistors in the chip than you actually need for your function. Okay. So how these cells are programmed? As I mentioned, basically you can program the interconnections, or you can program a memory. For programming the interconnections, typically there is a fuse-based programming. So there are two types of fuse-based programming: the so-called fuse and the anti-fuse. The fuse means that we have a circuit that normally is a short circuit, that that you can program only by transforming it in an open circuit, and you do it using it as a fuse. Basically, you let a high current flow to the fuse in order to blow up the fuse and open the circuit. So you typically have some interconnections with the thinner part. If you have a large current through this part, this thing goes high in temperature, it blows up, and you have an interrupted circuit, an open circuit. So you write the interconnections, you open an interconnections that was already there at the beginning, and of course you can only do it once. It's a write once process. Okay. The opposite of it is the so-called anti-fuse programming, and in that case you have a circuit that is normally open, and then you close it. For example, you can have two semiconductor region, this is SC and this is SC, that are separated by a thin dielectric, a thin insulator. In this case, this is an ono dielectric. Ono stays for oxide, nitride, and oxide. But for our purposes, it's just the dielectric. And then, in order to break the dielectric, you apply a large voltage between the two conductors. so that you basically uh, basically break down the electric between the two conductors, and so that you have a short circuit. Okay, and also in this case, of course, it is right once only. You cannot reverse it. Okay, so you start with so the use of FPGA is the following. You start with an FPGA, you put them into a programmer, a simple system that performs this programming operation. You decide what interconnections have to be opened or what have to be closed. Typically, you have either one or the other option, depending on the technology. And then you remove the FPGA from the programmer. You can put it on the board, on the circuit board in which you need it, and you're done. So it's a very fast procedure. Of course, it's since the cost of the FPGA is not small, is only convenient for very small volumes, very small number of chips. In the other two options that I mentioned here are the non-volatile FPGA and the SRAM-based FPGA. In these cases, what you do, you program a memory. In the case of non-volatile FPGA, you typically program an interconnection. And the SRAM FPGA, you typically program a lookup table. So this is typically a lookup table, typically, but not always. In this case, you program a non-volatile memory. Non-volatile I don't want to spend time on how a non-volatile memory works, because we have, but later today we will spend some time on it. So it's going to be clear. Both this and this other, both the non-volatile FPGA and the SRAM-based FPGA are reprogrammable. So they can be reprogrammed again and again and again. So it's a reversible configuration. So as opposed to the fuse-based, which is not reversible. Okay. So what is the type of logic that can be programmed? Typically, the type of logic that can be programmed in an FPGA is so-called array-based programmable logic, the PLA and the PAL. Most of you should have probably seen them in the basic class in electronics. You typically have an AND array or an OR array, and this configuration enables you to obtain any combinatorial function, and the behavior of the AND array and the behavior of the OR array can be configured by deciding if in all of these positions in which I put a circle, you have or you don't have a contact. By choosing if there is a contact or not in all these positions, you can program the AND array and you can program the OR array. Okay, so you can have any combinatorial function. That's it. You should imagine that in this situation, in the place of every cross, you can have a fuse or an antifuse for in the case of write once FPGA, or you can have a non-volatile memory that impose this contact or does not impose this contact, imposes this contact or not. Okay, so every contact can be programmed. The other thing that you can do with with programmable logic is the so-called cell-based programmable logic. So also in this case, you probably know that you can obtain any combinatorial logic with a lookup table. So a lookup table is a small memory bank. For example, if I want to program here, this is 0. If I want to program here XOR, so XOR is a logic gate that has 1 when the two input are different and 0 if the two input are equal. Okay, this is a logic gate that I know how to obtain with complex logic gate structure. But of course, I can obtain this operation also with a memory by having a memory here and a multiplexer here. So, which means that, for example, at the address 0, 0, I can write here the 0. At the address 0, 1, I can write here 1. At the address 1, 0, I write here 1. At the address 1, 1, I write here 0. So I have to configure this memory in order to obtain any lookup table I want. So any combinatorial network can be obtained by just having a multiplexer and by just writing a memory. And this is typically done in SRAM-based FPGA. In SRAM-based FPGA, this memory is an SRAM, typically, that can be written when the FPGA is switched on. Okay. These are just two pictures, just two examples of what I've shown. This is a gate array-based chip. You see the underlying structure is extremely regular. Then on top of it we have the interconnections that have been let's say that are the only part that have been designed. Okay, so only this this interconnection part is designed and obtained in the fabrication phase by only fabricating the interconnections. This more regular part is a memory subsystem that, of course, becomes much more regular because as usual, is an array. Everything is identical. Also, interconnections are not random. Okay. The SRAM-based FPGA is much more regular. As you can see, in this case, every small square here in this example is a small combinatorial functions with attached a memory to be programmed. So that every small combinatorial network, every logic gate is obtained by programming an attached memory. Yeah, okay. We can stop here.